Hello, this is Dr. Hanaa Assil, and this is Unit 6 of the Pearson Edexcel International A-Level Chemistry. This is the paper that was June 2022. So let's take a look at the questions and discuss the answers. The first question says, a student investigates two aqueous solutions, each containing a salt. Each salt has one cation and one anion. Solution A is blue and solution B is orange. Now, solution A, he added aqueous sodium hydroxide and he got a blue precipitate insoluble in excess. Now, what gives a blue precipitate insoluble in excess with sodium hydroxide? You should know that that is copper 2. So we probably have copper 2 something. Okay, then he added dilute nitric acid and silver nitrate and he got a white precipitate. Which one gives a white precipitate with silver nitrate? Remember, nitric acid and silver nitrate are tests for chloride, bromide, iodide. The chloride gives white precipitate, so what I have must be copper 2 chloride. Remember that the bromide gives cream and the iodide gives yellow. The white precipitate is separated from the solution. Give a test on the precipitate and its positive result to confirm the identity of the anion. We said it has a white precipitate with silver nitrate and we decided that that means that it is a chloride. Now, how do we make sure it's chloride? We take the precipitate and we add dilute aqueous ammonia. If it is chloride, it would dissolve. The precipitate dissolves to give colorless solution in dilute aqueous ammonia. If it was bromide, it wouldn't dissolve in dilute, it would dissolve in concentrated aqueous ammonia. And if it were iodide, it wouldn't dissolve in any of them. It doesn't dissolve in dilute and it doesn't dissolve in concentrated aqueous ammonia. So this is supposed to be chloride. It would dissolve to give a colorless solution. Okay, then he says I have another solution called B. And he says when he added aqueous sodium hydroxide, the solution changes from orange to yellow. And the gas evolves on warming, which turns damp red litmus paper to blue. Now, which gas on warming turns damp red litmus paper to blue? He's saying identify the gas. That is ammonia. So that means that my salt, I added sodium hydroxide and warmed gently, I got ammonia gas. And that means that my anion must be, my cation actually must be ammonium. Then he added dilute nitric acid and aqueous silver nitrate and he got a red precipitate. Now what gives a red precipitate with aqueous silver nitrate? You should remember that silver nitrate with dichromate salt gives a red precipitate. So this red precipitate is a precipitate of silver dichromate, and that means that the formula of the ions in the salt are, we said we have ammonium NH4 plus and dichromate Cr2O7 2-. Question 2 says, a student is asked to identify 3 colorless liquids labeled C, D, and E. The compounds are all non-cyclic and they are isomers with the formula C5H10O. The student carries out 3 tests on separate samples of each compound. Complete table 1 to show the observations that the student makes. Okay, sample C, he's telling me C is something that has this functional group. Can you see the functional group? This functional group. So it has a C double bond O and CH3. First of all, he did a test with 2,4-dinitrophenylhydrazine. And my question is, 2,4-dinitrophenylhydrazine is a test for what? You should know that it's a test for aldehydes and ketones. So both aldehydes and ketones give an orange precipitate with 2,4-dinitrophenylhydrazine. This one is a ketone, so it should work with 2,4-dinitrophenylhydrazine. Then he did a test with Fehling's or Benedict solution. Now, this is a test for what? You should remember that Fehling's or Benedict solution is a test for aldehydes. The Benedict solution is originally blue. If I have aldehyde, then it should give a brick red precipitate. But do I have an aldehyde? No, I have a ketone. So with the Benedict solution, there would be no reaction. The solution remains blue. What about iodine in sodium hydroxide? This is a test for what? This is the test we call iodoform test, and it is a test for having a group of C double bond O CH3, which is that group on the end of my compound C. So I do have C double bond O CH3, a ketone with adjacent methyl group, or actually an alcohol with adjacent methyl group would also give a positive result. So what is the positive result? If I have C double bond O CH3, I should get a yellow precipitate. Sample D, he says, is that functional group. Can you see the functional group? So obviously sample D is a secondary alcohol. Now, if I react 2,4-dinitrophenylhydrazine, would it work or not? Remember we said 2,4-dinitrophenylhydrazine is a test for what? We said it's a test for aldehydes or ketones. Is this an aldehyde or a ketone? No, it's a secondary alcohol, so there is no reaction with Brady's reagent. What if I do the test for Benedict solution? We said Benedict solution or Fehling's solution is a test for what? For aldehydes. Do I have an aldehyde? No. So with Fehling or Benedict, there would be no reaction. Then he has another sample which he calls E, and this is the functional group that we have. So this is what? This is an aldehyde. Okay. So when he reacted 2,4-dinitrophenylhydrazine, he got an orange precipitate. This is because I have aldehydes. What about Fehling's solution? We said Fehling's solution is a test for aldehyde, so I would get a brick red precipitate. This is test for aldehyde. Now, iodine with sodium hydroxide. We said the iodoform test is a test for what? It's a test for C double bond O CH3. Do I have that group? No, I don't have that group, so my solution will remain colorless. There is no reaction, no precipitate is formed. Identify by name or formula the pale yellow precipitate that forms when iodine and sodium hydroxide are added to sample D. We said this is sample D. It is a secondary alcohol. It reacts with iodine in sodium hydroxide, and that is because the iodine with sodium hydroxide is a test for the group where we have a CH3 next to a C double bond O, or a CH3 next to an OH on the neighboring carbon. So any of these, when we react them with iodine in sodium hydroxide, the final product is CHI3, and CHI3 is referred to as iodoform or triiodomethane. Notice it is CHI3, not H3. Okay, so CHI3, that means we replaced 3 of the hydrogens with iodine, and we still have an H on it, triiodomethane. The orange precipitates produced on addition of Brady's reagent to samples of C and E are called derivatives. The melting temperatures of derivatives are used to confirm the identity of compounds. Solids are recrystallized so that their melting temperatures may be determined accurately. Describe in outline the procedure for recrystallization of a solid. So if I have a solid and I want to purify it so that I can get an accurate melting temperature, I can recrystallize it. How do we recrystallize a solid? This is just crystallization, but I'm starting with a solid. So the first thing I need to do is add the solid to a small amount of solvent, heat to dissolve the solid. And then we're supposed to filter the solution, so we remove any impurities, allow the solution to cool, it would form crystals, filter the crystals through filter paper and funnel, wash with a few drops of the solvent, dry the crystals between filter paper. So basically we're doing crystallization, but we're starting with a solid. So I have to dissolve it in a hot solvent first, heat it up, and then filter and cool, it forms crystals. So these crystals should be pure crystals. The melting temperatures of the derivatives of the reaction of Brady's reagent with some aldehydes and ketones are shown. So he gives me the melting temperatures of these compounds, of the derivatives actually of these compounds. The melting temperature of the recrystallized derivative of sample C is found to be 138 to 140 degrees Celsius. So the compound sample C was this. This compound, we want to know exactly what its structure is. So this compound had a melting temperature of 138 to 140. Suggest the identity of this compound and justify your choice using the information at the start of the question and the data in tables 1 and 2. What did he say at the start of the question? Remember, we said it is a ketone, so I cannot have butanals, so the first two are wrong. It could be pentane 2-on. Can you see the structure of pentane 2-on? Pentane 2-on is actually a compound that has that C double bond OCH3 which we're looking for. Now, can it be cyclopentanone? No, because at the beginning of the question he said the compounds are all non-cyclic. So it cannot be cyclopentanone. So it's a ketone. He tells me that's a ketone. So it cannot be butanal, 3-methylbutanal or 2-ethylbutanal. So the first two choices I cannot choose. It could be pentane 2-on because this is something that has 5 carbons and it has a C double bond OCH3 which we're looking for. Now, can it be pentane 3-on? This is pentane 3-on. No, it's not pentane 3-on because it doesn't have that group at the end, C double bond OCH3. So actually, we should decide that it is pentane 2-on, especially that the melting temperature that he found, which is about 140, is close to the melting temperature on the table, which is 144. So we're going to decide that our compound is this one, pentane 2-on. Why did we decide that? Because this is a ketone, so it's not 3-methylbutanal or 2-ethylbutanol, and it's not cyclic, and it cannot be pentane 3-on because it doesn't have the C double bond OCH3, and its temperature is the nearest one to 140. Can you see how we decided it's pentane 2-on? Okay. The high resolution proton NMR of E is shown. So E was this one, something that is an aldehyde. The relative numbers of protons responsible for the singlet peaks shown are P equals 1 and Q equals 9. That means the peak at about 9.5 is due to 1 hydrogen, while the peak at about 1.2 is due to 9 hydrogens. Use this information and the results of the tests to draw the displayed formula of E, labeling proton environments. So we're looking for an aldehyde that has one hydrogen at 9.5. That is the hydrogen of the aldehyde. The C double bond OH, that is the hydrogen. So that means that I have 9 hydrogens that are equivalent. And remember that he told me that the compounds have the formula C5H10O. So that means that I want the hydrogens other than that of the aldehyde. I want all of them to be equivalent. So it must be something like this, in which we have the CH3s all bonded to one carbon. So I have a total of 5 carbons, 1 oxygen, 10 hydrogens. And it will agree with the NMR because the hydrogen of the aldehyde would be the one at P, and the 3 carbons carrying 3 hydrogens each would all be equivalent. He wants the displayed formula, and he wants me to label the proton environments. So the one he called P, that's the one at the aldehyde, the H of the aldehyde, and all the other hydrogens are the one at Q. Can you see how we labeled it? Question 3 says, brass is an alloy of copper. The percentage by mass of copper in a sample of brass can be determined by a 3-stage process. So stage 1 says oxidation of the copper to copper 2 ions with excess concentrated nitric acid. Then stage 2, reduction of the copper 2 ions to copper 1 ion with excess iodide. Then stage 3 is titration of the iodine produced in stage 2 against a standard solution of sodium thiosulfate. So the first question says, in stage 1, 2.53 grams of brass is carefully warmed with 25 centimeter cubed of concentrated nitric acid in a beaker. The equation for the oxidation is given, and he's asking state 2 hazards. In this experiment, giving the precautions you would take to minimize the risk associated with each hazard. What did he say? He said in stage 1, the brass is carefully warmed with concentrated nitric acid. Of course, if I'm using concentrated nitric acid, the hazard is that it is corrosive. So the precaution would be to wear gloves. He wants another one. What else did he say? We're doing a reaction that gives nitrogen dioxide gas. And any reaction that forms a gas, which is probably toxic, most gases are toxic, this we should do in a fume cupboard. So the other hazard is that the reaction produces nitrogen dioxide gas, which is toxic. Now, the precaution would be do the experiment in a fume cupboard. State what would be seen during the reaction. What was the reaction again? He reacted the copper with nitric acid. So this should give copper nitrate and nitrogen dioxide gas. Do you know the color of nitrogen dioxide gas? You should know that the nitrogen dioxide gas is reddish brown fumes. So one thing I would observe or I would see is reddish brown fumes of nitrogen dioxide gas. The other thing is when the copper reacts with the nitric acid to form copper nitrate, this copper nitrate forms a green solution, or actually it could be a little bit bluish, but it is a green solution is formed. Excess nitric acid must be neutralized before the iodide ions are added. So when we have excess acid, we need to neutralize it before going on to the next part. Sodium carbonate solution is slowly added to the cooled solution. The solution is neutralized when a faint precipitate appears. So just why the solution is cooled before adding sodium carbonate. So of course we're adding sodium carbonate to neutralize the acid. But then when you add carbonate to acid, what happens? It will bubble over because it's giving carbon dioxide gas. So we need to cool it so that the effervescence of carbon dioxide gas is not too vigorous. So we cool it to slow down the reaction so that the formation of carbon dioxide gas is not too vigorous. Ethanoic acid solution is added drop by drop to the neutralized mixture until the precipitate redissolves. Describe how this solution should then be made into 250 centimeter cubed of a homogeneous solution. So we have a certain mixture. I want to make it up to 250 centimeter cubed. And you should know that when we try to make something into 250, what do we use? We use a volumetric flask. Remember that the volumetric flask is a flask that has a mark. If we fill the solution to that mark, it is exactly 250. So we have a solution in a beaker. What should we do? Transfer the solution to the volumetric flask using a funnel. Then wash the beaker with some distilled water and transfer all the washings to the volumetric flask. And then we add distilled water to the volumetric flask slowly until the bottom of the meniscus is at the mark. And then we need to close with the stopper, shake, invert several times. So you're trying to mix the solution so that it is equally distributed. Okay. In stage 2, 25 centimeter cube portions of the solution from stage 1 are transferred into conical flasks. 10 centimeter cubed of a solution of potassium iodide is added to each flask. Copper 1 iodide is precipitated, so I get a precipitate. The redox equation is shown, and he gives me the standard electrode potentials for the Have equations for these reactions. Now use the electrode potential data to explain why the redox reaction might not be expected to be feasible. Okay, what do we have? We have the copper 2 plus going to copper plus 1. So that is my first equation. Now my second equation is the opposite of the one he has. So in order to calculate the E of the cell, I need to invert the second equation, and as a result, I should invert the sign of the E naught. So instead of plus 0.54, it is now minus 0.54. And this is the one that is correct, I minus going to I2. Now, to get the E cell, we add up these two electrode potentials, but the result comes out as a negative value. And you should know that if the E cell is negative, then the reaction we say is not feasible. So actually the reaction he's making, it shouldn't work. It's not feasible. But he's asking you to explain why you think, even though the E cell is negative, why do you think the reaction takes place? So, in fact, this reaction takes place even though the E naught is negative, or the E of the cell is negative. Why? If you notice, one of the products is a precipitate. So, as it forms copper 1 iodide, this comes out of solution as a precipitate. So, the equilibrium needs to shift to the right to form more products in order to replace the copper iodide that is removed from the solution. So this is why this reaction occurs. The product, one of the products, is a precipitate, so this forces the reaction to go to the right to form more products. The procedure in stage 3 is shown. The iodine produced in each flask from stage 2 is titrated. So we did in stage 2 a reaction that gives iodine. Now we're going to titrate this with sodium thiosulfate until the iodine color is pale yellow. And then we add a few drops of starch indicator. Remember, when we do a titration involving iodine, The indicator we use is starch, and we add it not at the beginning of the titration, but towards the end, because at the beginning the color is too dark and I wouldn't see any color change. So we wait until the iodine is used up, the color becomes pale yellow, then we add a few drops of starch indicator. Sodium thiosulfate is added drop by drop until the end point is reached. The titration is repeated until we get concordant results. Give a possible reason why the starch indicator is added when the iodine color is pale yellow rather than at the start of the titration. At the start of the titration, I have iodine, and iodine is dark in color. If I put starch, the iodine reacts with the starch. It should form a very dark blue-black color, and that would make the color change difficult to detect. So we wait for the amount of iodine to be less so that the solution is pale yellow, and then I add the starch. Give the color change at the end point of the reaction. Again, we said iodine is produced in the flask. So that is the first flask on the left. Iodine in solution is reddish brown. And then when we start adding sodium thiosulfate, then the iodine reacts with the sodium thiosulfate until only a very small amount remains. So the solution becomes pale yellow. Now, when the solution becomes pale yellow, then I add a starch indicator. Starch with iodine gives a dark blue-black color. So we add the sodium thiosulfate until all the iodine is used up. That means the dark blue-black color changes to colorless. So these are the changes in color when we do titration of something that has iodine with sodium thiosulfate. The results of the titration are shown. Complete the table and calculate the mean titer of the concordant results. So, experiment 3, of course, the titer is just the difference between them, so that is 26.45. Now, we said to get the mean titer, I choose only the ones that are concordant. Remember what we mean by concordant? The ones that are within 0.2 or less of each other. So the only ones that are concordant are experiment 2 and 3. Experiment 1 is too far away. So we do not include it in the calculation for the average. So the average is just the average of these two numbers, and that comes out to be 26.55, of course, centimeter cubed. The redox equation for the reaction between copper 2 and iodide is shown. The reaction of sodium thiosulfate with iodine is shown. Calculate the percentage by mass of copper in the 2.53 grams of brass. So we had brass and we put it in nitric acid, and we took this and reacted it with iodide so that we formed iodine, and the iodine reacts with the thiosulfate. Now, what information do we have? He says at the beginning of the question, he says, I have 0.095 mole per decimeter cubed of sodium thiosulfate. And we found that the average titer of the sodium thiosulfate was 26.55. That means I can get number of moles of thiosulfate. So the number of moles of thiosulfate is concentration times volume. The volume is divided by 1,000 to change it to decimeter cubed. This gives me number of moles of thiosulfate. Now I look at that second equation where we have thiosulfate with iodine. You'll find that the number of moles of iodine is half that of the thiosulfate. So the number of moles of iodine is half that of thiosulfate. But then if I look at the equation above it, the number of moles of copper 2 plus are twice that of iodine. So we again multiply by 2. And that gives me the number of moles of copper 2 plus, but that is also equal to the number of moles of copper metal, because according to that equation on top, the copper 2 plus is a 1-to-1 ratio with copper. but this is in 25 centimeter cubed. Remember that he made up the solution to 250 and he took 25 centimeter cubed of this solution. So the number of moles in the whole 250 would be that number times 10. And the mass is the number of moles times mR, and that is 1.601 grams. This was in what? In 2.53 grams of brass. So the percent copper in the brass is that over the total times 100, and that means I have 63.3% copper in the brass. Nitric acid reacts with iodide iron to form iodine. In another experiment, the nitric acid was not neutralized before the start. Remember, we said the nitric acid, we have to neutralize it first before we go on. Explain the effect on the value obtained for the percentage of copper. So if I don't neutralize nitric acid, that means I have some nitric acid in solution, and that means it will form more iodine than I should have. So I will have more iodine in solution than I should. And that means when I titrate it with thiosulfate, the titer would be higher. And that means that the number of moles of copper and percent copper would be higher than it should be. Are we following? Okay. Question 4 says limonene is a liquid hydrocarbon which has a boiling temperature of 176 and a density of 0.851. It can be obtained from orange peel using steam distillation. Label the diagram to show the direction of water flow in the condenser. You should know that in any condenser, whether we're doing simple distillation or fractional distillation or steam distillation, the water goes in from the bottom, comes out from the top. And if we say why, this is because we need the condenser to be full of water for more efficient cooling. Then he says, give a reason for using steam distillation to extract limonene. What do we mean by steam distillation? He has a flask containing water. He heats this water so the steam goes into the flask in which we have the orange peel. This is called steam distillation. This allows the substance to boil off at a temperature lower than it should be. So it boils at a lower temperature, and this is usually used if the substance is likely to decompose at high temperature. So we don't want to heat it to a very high temperature or it would decompose, and that is why we use steam distillation. The distillate may be collected in a pear-shaped flask. Complete a label diagram showing the distillate. You should show clearly the limonene layer. Now, what we have would be two layers, the limonene and water. And if we go back to the beginning of the question, he said that the density of limonene is 0.851. That means it is less than 1. Remember that the density of water is 1. So anything with lower density than 1 would float on water. So when we have the limonene with the water, the upper layer is the limonene and the lower layer is water. Limonene exists as optical isomers. Identify the chiral carbon on the diagram. Remember, we said optical isomers are obtained if the substance has a chiral carbon. Now, what's a chiral carbon? A chiral carbon is carbon that has 4 different groups. So where does this apply to this diagram? If you look at this carbon, it has 4 bonds going to 4 different groups. So that is my chiral carbon. The limonene extracted from orange peel is D-limonene. State how the presence of a single optical isomer could be confirmed, naming the apparatus used. No experimental details are required. Remember, if we have optical isomers, the definition of an optical isomer is that it can rotate the plane of polarized light. Remember that an optical isomer, if it is placed in a polarimeter, so he's saying name the apparatus, this apparatus is called a polarimeter, and we have a source of light that is polarized. So if we have an optical isomer, it changes the direction of the plane polarized light. A student obtained 1.20 centimeter cubed of limonene. Calculate the amount in moles of limonene. How do we get number of moles if I just have the volume? Well, this is a liquid. He gives me the density, and from the density, I can get the mass. And this is my compound, so I can get the MR of this compound. So, first of all, we have density. You know that density is mass over volume. So if I want the mass of the liquid, it is density times volume. Remember, we said the density is already in gram per centimeter cubed. So my volume can also be in centimeter. Actually, it has to be in centimeter cubed. This gives me the mass in grams. Now, in order to get number of moles, I need mass over molecular mass. How do I get molecular mass? I look at this compound. What is its formula? You will find that its formula, if you count all the carbons and hydrogens, they are C10H16. So you can get the MR of that. This comes out to be 136. So now I have the mass and the molecular mass. I can get the number of moles. Mass over molecular mass, this gives me the number of moles. Limonene reacts with acidified potassium manganate. Give the color change for this reaction. Remember, if I react anything with potassium manganate is originally purple. When it reacts, it changes from purple to colors. And the last part of the questions says, draw the structure of the organic product which might be expected when excess acidified potassium manganate reacts with limonene. What was limonene? This was limonene. And you should know that when something that has a double bond reacts with an oxidizing agent like potassium manganate, what happens is the double bond is opened and we get diols on those two carbons. So each of these double bonds, he says I have excess, so each of the double bonds is broken up to form diols. So this would be the structure of my product. And that's the end of this. I hope this was useful to you. Thank you for listening.